from thesis H, and we are team Heimta N. These are our comrades. This is Mark, Michael, Jonathan, Porch, and I'm the reporter today. My name is Neil.
Hello everyone. I'm 我是小美女队 I'm the captain of our team, and I will report. Hello.
好，然后两队猜拳，第一个是 A 还是 B？ 赢的是 A， 那就先报告。
Okay, good morning ladies and gentlemen, and today I'm going to introduce our topic, which is ring Euler. Okay, so first is our problem statement. An oiled horizontal cylindrical graph rotates around its axis. And from the question, we can see that it is required for us to make a ring which has an inner diameter roughly twice the diameter of the shaft, and put the ring on the shaft. And depending on the tilt, it will move along the shaft, and we can investigate this phenomenon. Okay, and so our presentation layout would be, firstly we'll introduce our problem layout, and then we'll have our hypothesis and our theoretical model. And third, we will have our experimental data, and then fourth, we'll have our conclusion, and we'll discuss the correspondence of our data and our future direction. Okay, so our problem layout, firstly, is the structure of our device. As we saw from the problem statement, we have a motor connecting to a shaft, and the shaft and the ring are both rotating at an angular speed. We mark them as omega-1 and omega-2 respectively. And then we have the radius of the shaft marked as R1, the inner radius of the ring marked as 2 times R1, the outer radius of the ring marked as R2, the horizontal speed of the ring moving on the shaft marked as V, and then the angle between the ring and the perpendicular direction of the shaft marked as theta. Okay, and this is how our device actually looks like. You can see there is a motor, there is a shaft, and there is a ring. Okay, so next page. Let's see how it actually functions. So as you can see, the ring will start rotating while the shaft is rotating, and it will move back and forth down the shaft. Next page. Okay, so our goals are to investigate the relationship between the following parameters and the movement of the ring. First is the shaft rotation speed, and next is the tilt angle of the ring. Our independent variables are first the rotation speed of the shaft, next the diameter of the shaft, which is relevant to the inner diameter of the ring, and then thirdly is the tilt angle of the ring. Our control variables would be the material, which is cardboard, and the thickness of the cardboard disc, which is 1 mm, and the outer diameter of the ring. Our dependent variables would be the speed traveling down the shaft and omega of the ring. Some points for clarification are, firstly, air resistance is something that we should account for, but due to the complexity, we will view it as an ignorable constant in our model. Secondly, we'll assume the ring to be an ideal flat disk, and assume the density of the pole to be evenly spread out. Thirdly, we assume the mounter's output force to be constant, therefore the speed of the shaft would also be constant. Next is our hypothesis and our theory. The concept involved would be, firstly, the friction between the ring and the shaft. Secondly, the relationship between omega-1, omega-2, and theta. And then we will introduce our first hypothesis. Then we will have our relationship between Vx and theta introduced. And then we will have our second hypothesis introduced. The friction between the ring and the shaft. So the device is a shaft with a ring around it. Firstly, when the ring is first put onto the shaft, the ring is somewhat stable compared to the shaft, so it will have a kinetic friction which will cause it to start rotating, and it will have an angular acceleration which we marked as alpha in this picture, which would be in the same direction as omega-1. Once the ring is accelerating, the kinetic friction won't change it, but once it gets to a point where there is no relative motion on the y direction, as you can see in this picture, the kinetic friction will reduce to 0, which will cause it to stop accelerating. So this comes our first hypothesis. When a ring accelerates to a point that omega 1 times r equals omega 2 times 2r times cosine theta, the rotation of the ring steadies and the friction on the z-axis reduces to 0 because of no relative movement. Considering all the parameters that will affect the overall velocity of the shaft, we can reduce this to one formula that is describing the velocity of the ring, which is omega 2 cross 2r plus v minus omega 1 cross r, which describes the relative velocity of the ring. And we can spread it in two vectors, one on the x direction and one on the y direction. And considering that friction comes in the opposite direction of relative velocity, we can describe the direction of overall friction using this vector. Therefore, as mentioned formerly, we can see that when the ring reaches an equilibrium, the friction on the y direction will reduce to 0. And so you can see we can divide friction into the x component and the y component, and the y component will reduce to 0. So next, let's discuss the x component of friction. The relationship between Vx and theta. As mentioned formerly, we have an x component of friction, which will cause an acceleration when the ring is first placed onto the shaft, which will cause an acceleration in the horizontal direction. So it will accelerate due to kinetic friction, and when it comes to a point when the horizontal speed comes to omega 2 times r times sine theta, from this point and on, the relative speed between the shaft and ring is 0, which will cause the kinetic friction reduced to 0. The same situation happens even if you give an initial speed to the ring. It will still reduce to a point where there is no relative movement. So as you can see, when we reduce the y direction friction to 0 and the x direction friction also to 0, we have our second hypothesis, which is at equilibrium, the horizontal speed of the ring will correlate to its omega according to this formula. V equals omega 2 times 2r times sine theta. Thus, the horizontal velocity will reach a maximum, and theoretically, the ring will reach a point of 0 friction. So next comes our experimental data. Firstly, we are measuring the omega 1, which is the rotation speed of the shaft. We mark the shaft with an aluminum foil and use high-speed camera to analyze its motion and use tracker to record its speed. Now here is our first experiment. We input different voltages into the motor and measured its relative omegas. Okay, our experiment 2 is measuring omega 2 under different thetas. And we have the same measuring method as experiment 1, except we use a marker to mark the ring and recorded that instead. And we control omega 1 and measure omega 2 under different thetas, and we analyze the diagram of omega 2 and the inverse of cosine theta. So this is our data, and this is our diagram. We will review the relationship between our diagram and our hypothesis later. Next is measuring Vx under different thetas. Similarly, we are still using a camera to record the speed of the ring moving down the shaft, and then we use tracker to analyze this speed. And so this is our diagram of the relationship between Vx and omega 2 times sine theta. So here is our conclusion in our discussion. Firstly is the correspondence of our data with hypothesis 1. As we can see in this diagram, our hypothesis was omega 1 times r equals omega 2 times 2r times cosine theta. And in this diagram, we can see that the correspondence between omega 2 times and the inverse of cosine theta is correlating to our hypothesis, which is the omega 2 is proportional to the inverse of cosine theta. And our correspondence of data with hypothesis 2, which was Vx equals omega 2 times 2r times sine theta, which we also found our data supporting our hypothesis, which is Vx would be proportional to omega 2 times sine theta. So our conclusion would be, through our hypothesis and our corresponding data, we've affirmed these two these two relationships between omega and Vx, which is omega 2, is proportional to the inverse of cosine theta, and Vx is proportional to omega 2 times sine theta. Now, there are still some errors within our data to our hypothesis, and we figured that these could be because of two things. One is that the theta would vary when the ring travels down the shaft because of several reasons. One is vibrations, and one is like the wind and the air resistance, which we ignored in our model. The second is which is camera and tracker, would cause some deviations while programming it. And looking ahead, we ought to optimize the most stable design to make it have a steady rotation and investigate the change of theta as it hovers back and forth on the shaft. So thanks for your attention.
10 minutes for safety to report.
Hello everyone. I'm from Senior High School. 我是小可爱. Today I will report the ninth problem. Candle in water. This is the problem statement. Add some weight to a candle such that it barely floats in water. As the candle burns, it may continue to float. Investigate and explain this phenomenon. We see light a candle in water. And when it burns, it may continue to float. And we think that is it different from the candle burning in the air? So we want to investigate how different and why it continues to float. And this is my outline. First, I will introduce the experiment. And I will show you the setup and the definition I define and that the phenomena I observe. And then I will show you the parameter and the result I get. And then I will show you a theory. First, I will introduce the blurry body diagram of the candle and the candle's motion. And then I will show you the different when the diameters of the candle is different. What will appear, and then I will show you the conclusion. But first, I will show you the experiment. This is our setup. We put a scale under the setup first, and to record the variation of the mass of the candle, and then we put a camera between this system and record the motion of the candle. And first I will show you the phenomena of the candle whose diameter is smaller. You can see that the candle float upward. But at last it sank when water ended. And then I will show you the candle whose diameter is bigger. And when the fire goes out, the candle didn't sink and it floated at its position. And then I will show you the definition. We define that barely float is that when the candle added with some weight under it, and it can bear only 0.5 gram more. If we add so much weight on it, it will sink as soon as possible. then we define that the angle is that the surface tension whose direction is vertical. And then we define that the burning rate of the candle is that the mass decreased by the flame and divided with time. And this height we define it as the displacement of the candle, and we'll measure how different it is. And this is our parameter. First, we change the length of the candle, and then we change the diameter of the candle. This graph we get is that we observe the displacement of the candle whose length is different, and we can found that the 3 centimeters one is float obviously, and then I will show you the variation of the candle of its mass. And we can see that mass decrease is very steadily, and the 1 centimeter one its mass decreased faster. And this is the graph we change the diameter of the candle. We can found that the data is so complex because we have some error in this, but we can also see that the 1.831 is more and we can see on it, and this is the mass, the variation of the mass of the candle, and we can found that the 4.83871 and its mass decreased faster. And then I will show you a theory. This is the free body diagram. We draw that the candle before it starts to burn, and we can see that buoyancy and gravity of the candle is the same, and there's a surface tension to bear this candle and make it barely float in water. And then when the candle starts to burn, you can see that there's a bowl shape was produced by the flame. And as the candles can start to float, and we can draw this free body diagram as it. Because the mass was consumed by the flame, but the volume of the candle under the water is also the same, so the buoyancy is the same, but gravity decreases, so the candle will go upward. And this, I will explain the bowl shape. And the bowl shape was produced because the flame will hit the air, and the water will make the edge of the candle cold. So there's a bowl shape was produced by the flame. And we found that the bowl shape was different between the bigger diameter and the smaller diameter, because when the fire will make this side burn, and we define it the diameter of diameter of the candle is the big D, and the diameter of the bowl shape is small d. And we found that this is the 3.44 centimeter one, and we found that the bowl shape is the diameter of the bowl shape is less than the diameter of the candle. So the water can come in and it won't stick. And we can also see that the diameter, the candle whose diameter is smaller, and the water will come in the bowl shape if the edge was broken by the flame. And we can find that the range of the boundary diameter is 1.83 and 3.44, and the candle won't sink in this range. And this is our conclusion. The bigger the diameter is, the harder the edge is broken by the flame. And we found that the range of the boundary diameter is between this one. And thank you for listening.
We have 2 minutes for short questions preparation. Okay, time's up. Time for TV to ask Team A some short questions. You have 2 minutes.
Could you explain your theory again? And that page will show you a free elastic diagram.
Sorry.
So you want me to introduce which part of the theory? Sorry.
The cardboard on the rod and the omega and the omega 2.
Sorry, can I use the blackboard?
Get out here.
So initially it would be a shaft which is rotating at a speed of omega 1, and then you put the ring onto here. And then because it is rotating in this direction, and it will cause a relative movement. So the relative movement is in this direction, and we will have a friction in this direction, which will cause an acceleration. Okay.
I see that you throw a force
What I mean is because there will be friction in this direction and in this direction, because there would be a tilt to the perpendicular direction, which we mark as theta. Yes, so that would be a force of friction.
Okay. Time for Team A to ask Team B some short questions. 2 minutes.
Okay, firstly, is your method of measuring the mass consumed using the scale on the bottom of your flask? Yes or no? Yes, okay. Secondly, are you assuming that the mass changes when the volume doesn't in your theory? Yes or no?
No, I can't. But I can use the density of the candle too.
No, what I mean is that I saw in your presentation that you assume the candle to be in a cup shape, so the water won't go into the little volume inside, and you're assuming that when the mass changes, the volume doesn't, so the buoyancy doesn't change either. Is that a yes or no?
Yeah.
Okay, and thirdly, are you assuming that your candle would, when the flame burns down the candle, are you assuming that it will always be in a rectangular shape of the volume?
Now I can't gather, but I will do by burning that candle, and I will, after 1 minute, I will make a flame go up, and I will measure the.
Okay, we can discuss that later. And then fourthly, how many variables do you have?
2 times.
And sorry, how many variables do you, I mean, like how many things are you gonna change and how many experiments?
2 parameters.
Which two?
I get the length and the diameter of the candle.
Sorry, the first one again?
The length and
Oh, the length of the candle and the diameter of the candle. Okay, so you're assuming all of your candles have the same density. Have you measured the mass of each and every one and calculated the density?
yes.
Okay, thank you.
Okay, time for, you have 5 minutes to preparation. Okay, time's up. You have 8 minutes for discussion, and the first 4 minutes is the questions for leaf oil. And the next 4 minutes for the candle in water. Let's go.
Could you use you show your theory and draw the free body diagram? So now could you use your theory to explain how it turns its round?
Can you show the video? So responding to your question, why it will turn to the other direction is because when it travels down the shaft and so when it touches the other side, it will have a force which the other side gives it and it will turn to the other direction. So when it free flows on the shaft, it will turn to another direction. Only when it hits into something, it will turn to another direction.
Okay, so you think that the friction is kinetic friction, so but I think that the cardboard will the cardboard jump up and down on the rock when
The cardboard, because when we first put the cardboard disc onto the shaft, it will have some turbulences. But when it reaches a point of equilibrium, it will not jump up and down, and it will touch the shaft. The ring will touch the shaft on the upper part, so it would be like. It would be like the shaft is here and the ring will touch it here, and this will be the hole. So it will touch it in the upper part and it won't jump up and down. This is what we observed through our experiment.
Okay, so how do you define the cardboard will go this direction and then it will change its direction when it hit the wall you set,
Yes.
right? So could you draw the diagram to explain why it hit the wall and then change its direction?
Okay. So basically, the ring will touch the side of this and it will give it a force to let it go to the other side. And one thing I wanna clarify is that much of our theory would be focused on trying to define the motion when it free flows on the shaft. We're not entirely focusing on when it touches this point.
So you define that it will change the direction when it hit on the floor. So how do you define the problem statement? The problem statement shows a cardboard on the rod and it will change the direction, but it didn't. It didn't say that it will hit on the floor. So I think that it will change the direction by the force when the cardboard hit on the floor. So don't you think that the rod will give the force to the cardboard too?
Sorry, I'm not entirely understanding your question. Okay, so firstly, thank you for your report. I think it was very refined and it was great. You had a clear layout and introduction of the problem, and you displayed your experiments really clearly, and you had a large amount of data. My major points of discussion are, firstly, how do you ensure that the candle is on the stage of burning throughout the process? In other words, how do you ensure it to be at a constant state of bearing 0.5 grams more of buoyancy? How do you ensure that through the whole process of your experiment?
I define barely floating as when we add the weight to the candle and make it put in the water, and we will use the needle to put some water on it, and when we add less than the 0.5 gram, it will sink fastly. So we think that that's very good because it will sink.
Firstly, where did you get that amount 0.5 gram from? Did you just assume it, or is it from a reference?
We define this range because we do measuring experiments and we get this data from.
So you're just assuming it?
Yes.
Okay. Secondly, do you think that the hot air simply moves upwards because the candle top will concave down, and would it cause some sort of circling air in the cave you just created in the candle? Because you're assuming that the hot air would move upward, which would not cause other turbulences. Would you think that the hot air might cause turbulences when it is circling around in your concave?
I agree with that, but I think the force of the air is too small than the buoyancy and the gravity decrease, so I ignore it in my theory.
Okay. Thirdly, we know as a candle burns, it would turn from solid to liquid to gas. Have you measured the density of liquid candle oil? Is it the same as the density of solid candle? Because we can see as it burns, it would evaporate. It would evaporate through a liquid state first. So, is your density fixed?
I only measure the solid candle. The density of the solid candle is that 0.8.
Okay, so you didn't measure the density of liquid candle oil.
Yes.
Okay, so I figure that this might be a point that you could go on further into this experiment. You can change is that you can measure maybe the liquid candle, because the density will not be fixed if it's according to your theory. Okay, and fourth, how about the water evaporation and other mass changes around the candle flame? Are you, because you're assuming that the buoyancy won't change, but these little things can cause a buoyancy change.
I didn't say that the buoyancy will change. I said that the gravity will change because the mass was decreased by the flame. So.
But your volume doesn't change.
I mean that the volume under the water didn't change.
The buoyancy won't change.
Yes, the volume under the water and to water, the volume of the candle didn't be different.
Okay, thank you.
Okay, you have 3 minutes preparation for the conclusion. Okay, time's up. And now for the team B to make a conclusion first.
First, I think that the reporter's theory is very complete, but I think that he should use this theory to explain to fit with the data. And I also think that the definition of the problem statement is that it will change the direction in the process in the cardboard move. So I think that the reporter's definition is different from the problem statement, and he used the omega to explain his experiment. But I think the kinetic friction and static friction is also important as the omega. So I think reporter can investigate it further. And I also want to explain my experiment again. I find the density of the candle, of the solid candle, but I didn't find the liquid, so I will do it further, and then because I can measure that the force of the air now, and I think it's less than the gravity decrease, so I ignore it and okay. That's all. Thank you.
2 minutes conclusion for team A.
Okay, so for our conclusion report, first is our discussion with the candle in the water. We pre-understood your basic theory, and we thought it was pretty good, and we discussed the points on the density and your parameters. And then what we learned from your explanation is that we need to consider the surface tension in addition to your buoyancy, and hope it would be further improved and discussed in the future. And also, we discussed on some points that you could improve on your experiment, and some points that you could do in further experiments. So secondly is our own topic, which is the ring oiler. We have 2 hypotheses, and our discussion points are when the ring hits the edge, and some definitions, some variations in the definition of the topic. And what we understood from the topic statement is that the reason that it has, the topic statement is trying to state that the reason why it will go in a certain direction is because there was a tilt angle when you first put the ring down. But perhaps your definition was different from ours, and we had a different understanding, but we can discuss on that later. And our future improvement would be the perfection of our experiments, and we would possibly make theoretic models of different stages in the motion, including when we first put it down, and when it becomes constant moving on the shaft, and then when it when it collides with the border, and what the forces would be like. Thank you.
Okay, 5 minutes for jury to ask questions.
不好意思啊，我还是用中文发问哈。你看，先请教一下 A 队，就是说，假设他们有摩擦，你有做摩擦力的时候，然后
假设它没有动摩擦力的时候，基本上它应该是，它会维持一个就是一个稳定的转速跟一个稳定的，就是横向速度在做motion， 因为它没有其他的力会影响到它的转速，除了空气阻力是我们在这个model 里面不讨论的一个点。
谢谢。那我想请教一下对，就是说这个蕊芯只要放大跟大一点跟小一点，那在加热空气应该会不一样。那我想请教一下，你觉得蕊芯大一点跟小一点，对这个实验会不会有影响？
那个蕊芯如果变长的话，它的火焰
不是，是直径变大。蕊芯粗一点跟细一点。
有可能，因为火焰如果改变，这个它整个对流就会不一样。所以我觉得可以研究，但是我们现在还没有考虑到这一点。先考虑直径跟长度的关系。
因为我刚刚没有听清楚你对对流的解释这一块，可以再稍微帮我解释一下吗？对流这一块。
对流就是它火焰会加热空气，然后它火焰上方空气被加热之后就会上升，然后一旁冷空气会补进来，然后这在空气中的时候，它的确会形成凹槽，但是它会被破坏掉。然后，但是在水中的时候，水会一直冷却蜡烛的边壁，所以它的凹槽会一直存在。
谢谢。
好，我先问一下那个 A 队哈，就是我觉得理论写的不错，然后可是我只想问一下一件事情，就是我看你在动画模拟的时候，其实对高中来讲，都是粒子等于就是反射，可是很明显这个题目也是不简单嘛。那我是问你，是说你在这个研究，你主要研究这主题的动机到底是什么？或者说你在实验有什么新发现，或者是跟高中所学的有没有一些不同的地方？这样子，想听听一下你的心得，这样子。
我觉得主要就是一个。我觉得主要就是一个，就是因为它的这个旋转加上平移，它会有一个就是双重方向的摩擦力。那，就是我们在这个实验里面主要就是学到就是它的，因为它是一个，就是它的转速跟那个，就是它的 omega 2跟 omega 1不会是同向的，所以它是一个比较复杂的一个摩擦力，还有它的转速的一个关系的讨论。那我觉得就是在讨论这个。过程中要去把它用在脑中把它模拟出来，然后把它写出来是非常好，是我觉得还蛮有挑战性的这样子，就是我觉得是学到最多的一点。
好，那我想问一下第一个是说，我觉得你们的实验参数找得很仔细，找到表面张力还有所谓的很多质量跟长度的一些参数。那我想问说，你们在找这些参数，你们怎么会找这参数？这些参数会影响到什么？会影响到什么实验的结果？就是你们就是找寻这些参数的动机到底在哪里？这样子。
因为我们一开始就是定义 barely flow 是什么的时候，就是我们目前还没有做到让整颗蜡烛都是在水面下，就是连它的表面都是在水面下。所以我们后来决定定义说，那它就是它只能最多再承受一点点重量就会掉下去，就是勉强的浮动在水面。然后我们之所以会找寻那个直径蜡烛的直径跟长度，直径是因为它的凹槽跟直径的关系，可能会影响到它的沉或者是因为小直径它的凹槽半径很接近于它的直径，或者是很接近蜡烛的直径，或者是大于，所以它有可能会被破坏掉，然后水就流进去凹槽里。然后长度是因为我们想这个深度凹槽深度会不会有关系，但是我们现在还没有确切量到那个深度。
好。
那还有老师想问你吗？那就请各位老师评分。来，首先是 A 队。10分。 9分跟8分。好，我们谢谢两个队伍跟老师。